Hello everyone, we would like to introduce our e-voting application based on homomorphic encryption, blockchain, and decentralized tallying on Peerster. The presentation will follow by project requirement, system design and implementation, technical details such as homomorphic encryption, blockchain, and then we will continue with demo and conclusion. Now let's take a look at the project requirements. Our project aims to build an e-voting system with the following properties, such as open auditability, anonymity, reliability, trustworthiness, and low coercion.
So about the system design and the implementation, we take reference from the heroes, and based on this, we make the whole system more decentralized and use the blockchain to store the votes. For the first step of the vote election initialization process, the creator will create the election and pass the information to the independent server, which we are fully trust. And then the independent server will generate the public key and split the secret to the partial private and send to the trustee. And also, from the start, the independent server will generate authenticated secret to the trustee and for the further authentication. So the trustee will receive this and it will partially decrypt the encrypted vote and pass it to the tallier in the future. So when the voter starts to vote, it will encrypt the election with the public key, and by the end of the election, it can view the results of the election. And the tallier, when we get the signal from the creator that to create the partial decrypt factor, it will homomorphically generate the voting result and return it to the voter. About other components, we use the lightweight server and database to maintain the user management backend.
As we have mentioned before, we use homomorphic encryption in our system. Homomorphic encryption, with the details listed in the setup phase, provide a way to preserve the privacy of user votes in our e-voting system. Now let's come to the blockchain. It will contain two phases, authentication and consensus. The blockchain in our project contains the nodes in the network as trustees. Trustees are peersters in our system. The goal of our blockchain is to build a universal, accurate, non-modifiable, and robust ledger of encrypted vote at the end of the election. Now let's take a closer look at the authentication part. The problem in our system is that some untrusted peerster may try to promote some fake vote into the system and let the system crash. The solution in our system is to let the trustees to obtain some secret from the independent servers. They then use the non-interactive zero-knowledge proof to prove their status, to prove their trustness, and then authenticate themselves in the system. Therefore, only the trustees will be able to promote vote to others. The aforementioned process can be described in the following figures. Now let's talk about the consensus. Our goal, as mentioned before, is to build a blockchain with accuracy, universality, non-modifiability, and robustness. Then we will come to the question, do we need some complicated algorithms such as proof of work, proof of stake to implement our blockchain? Thanks to our assumption and homomorphic encryption and decryption, we don't need those complicated stuff. For example, the proof of work is not needed since the trustees collaborate instead of competing with each other to build a ledger. This motivates us to build such a simple consensus algorithm as illustrated in the figure. For instance, in such a typical round of consensus, a peerster may promote some vote to the others and receive the vote from other trustees. When they receive all the proposals from the peers, it uses some decision algorithm to select a universal proposal in the current round and put it into the blockchain. Some technical details including the verification of vote are not listed on the slide. Okay, now let's come to the demo part. The conclusion is that we have succeeded in implementing an e-voting peerster based on both homomorphic encryption and blockchain, and this system guarantees anonymity, trustworthiness, and integrity. The future improvement might be auditing implementation. Thanks for your watching.
Hello everyone. We would like to introduce our e-voting system based on homomorphic encryption, blockchain, and decentralized tallying on Peerster.
Basically, this is our running script. So we clean the port, cleaning the backend database, run the backend server,
and start the tallier, run the Peerster, and give some time for the independent server to send the secrets to the Peerster. And finally, we run the voter, in 3 voters actually. Okay, in our showcase, we will have 3 legitimate Peersters, which will handle the blockchain building and consensus reaching. In order to review our functionality of this project, we also have an untrusted Peerster, which will try to promote some invisible proposal into the blockchain. So now we move on to the technical section of our election. We will first create voters. These are people that take part in an election, and we already have set up a bunch of trustees that are already connected to the whole network. A trustee is a person that holds the partial decryption key, and basically whenever an election is created, a new public key is created for it, and the secret or part of it are being sent to these trustees. And these trustees at the end are in charge of generating partial decryption factors, and they can run the result at the end. We are doing this so that we can ensure privacy using homomorphic encryption, so that no trustee can know the individual votes of a voter, but they can only know what is the final result. So as long as there is at least one trusted trustee, we are the election is private. Now we have a first voter that has created an election, and for example, let's assume that he's asking what is your favorite US president, and he's inputting multiple choices such as Clinton, Trump, or Obama. And the idea is that by inputting these choices, he's actually asking other people what they could vote on these. Okay, now perhaps this guy wants to select the favorite basketball players among the history, and now he submitted the election. Perhaps the other guy say Ali want to provide another election. So the first question he will propose is his favorite course at EPFL. The choices are NLP, machine learning, and distributed information system. Perhaps he also want to ask another question. So for instance, his favorite Switzerland city. The choices are Zurich, Bern, and Geneva. Okay, now we have 2 sample elections. Let's take a look at the public key and the private keys. So basically, this is the public key that's generated for the voter to encrypt their vote, and there has been a different separate private key for the partial decryption for the trustee. So let's look back. If we look at the election tool, the set of public and private key are totally different, and they do not overlap. So for each election, we have a different encryption. So we can find out that only the creator of the election have the right to stop the election. So we can see for the Liangwei, he didn't have the right to stop any election. So basically, let's start voting. We vote for the first one. So after that, we try to view the result, but we cannot get the result because the creator has not ended the voting, so the election, so we cannot get the result. So after the creator and the result, let's have a look at this first. Okay, so let's take a look at the blockchain. The blockchain will handle the recording of the vote proposal by the voters. We can see in the blockchain visualization, there are already 3 voting records. It corresponds to our previous exercises. Now, for instance, let's say we have an untrusted Peerster who tries to promote some invisible proposal, and we can see that our non-interactive zero-knowledge proof, which can authenticate the Peersters, is now able to capture this fake post. The error message is already presented in the error log. So now let's go back to where we stopped, and now we want to stop the election. So we sent the signal of stopping, and it triggers the trustees to send their partial decryption factors and tally the votes by an independent party. So now we can see the favorite US president, they are equally likely, but the favorite basketball player, they're all voted for Kobe, which do confirm the individual votes that we had. Thank you.